Deep Learning, as presented by Team Hackathon.
My name is Megan Bond. I am the group captain, and I will be covering the introduction and supervised learning.
Deep learning grants computational models that are made of various layers that learn depictions of data with various levels of reflection. These strategies have devotedly addressed the state of the art in speech recognition, visual item confirmation, object recognition, and various fields such as drug disclosure and genomics. Deep learning tracks down dispersed structure in huge educational assortments by using backpropagation computation to show how a machine should change inside limits, which are used to calculate the depiction in each layer from the depiction in the past layer. Deep convolutional nets have accomplished forward jumps in dealing with pictures, video, talk, and sound, while irregular nets have shed light on progressive data like text and talk. Conventional machine learning strategies were limited in their ability to manage typical data. It has turned out to be proficient at tracking down plans and high layered data and is accordingly relevant to various areas of science, business, and government. As well as beating records in picture affirmation and talk affirmation, it has beaten other simulated intelligence techniques at predicting the activity of potential medicine particles, taking apart molecule smasher data, reproducing mind circuits, and predicting the effects of changes in non coding DNA on quality enunciation and affliction. Perhaps more amazingly, deep learning has produced extremely uplifting results for various endeavors in typical language understanding, particularly topic portrayal, feeling assessment, question tending to, and language translation. We envision that significant learning will have significantly more victories not long from now, since it expects close to no planning in the most difficult way possible. So it can, without a doubt, take advantage of extensions and how much open estimation and data there is. The generally perceived kind of artificial intelligence, deep or not, is overseen learning. Imagine that we want to develop a structure that can bunch pictures such as a house, a vehicle, an individual, or a pet. We first accumulate an enormous enlightening file of each named with its group. During setting up, the machine is shown an image and makes an outcome as a vector of scores, one for each characterization. The machine then changes its inside adaptable limits to reduce this mix-up. These adaptable limits, much of the time called loads, are real numbers that ought to be noticeable as handles that portray the data yield ability of the machine. In a typical deep learning system, there may be endless adjustable burdens and numerous considerable number checked models with which to set up the machine. To fittingly change the weight vector, the learning estimation calculates an incline vector that for each weight shows by what aggregate the mix-up would addition or decline, expecting the weight were extended scarcely. The weight vector is then changed the alternate way to the slant vector. The objective capacity tracked down the center worth of overall the readiness models ought to be noticeable as a kind of lopsided scene in the high layered space of weight values. The negative slant vector shows the course of steepest plunge in this scene, taking it more like a base, where the outcome botch is missing the mark overall. Before long, most experts use a technique called stochastic tendency dive, SGD. This includes showing the data vector.
Backpropagation to train multi-layer architectures procedure to compute gradient of an object function with respect to the weights of the multi-layer stack of modules is nothing more than a practical application of the chain rule of derivatives. The key insight is that derivation of the object with respect to the input of a module can be computed by working backwards from the gradient with respect to the output of that module. The backpropagation equation can be applied repeatedly to propagate gradients through all modules. Starting the network procedures its prediction. Where the external input is fed, once these gradients have been computed, it is straightforward to compute the gradients with respect to the weights of the. Many applications of deep learning use feed-forward neural network architectures which learn to map fixed size input to fixed size output. To go from one layer to next, a set of unit compute weighted some of their inputs from the previous layer and passed the result to a nonlinear function. At present, the most popular nonlinear function is a rectified linear unit, which is simply the halfway rectifier. In past decades, neural nets uses smoother nonlinearities, but the rectifier linear unit typically learns much faster in networks with many layers allowing training of a deep supervised network without unsupervised pre-training units that are not in the input or output layer or conveniently called hidden units. The hidden layers can be seen as distorting the input in a non-linear way so that categories become linearly separable by the last layer.
Everybody, my name is Rima Dev, and I'll be talking about convolution neural networks. Convolution neural networks are everywhere. It is arguably the most popular deep learning architecture. Now, the recent surge of interest in deep learning is due to the immense popularity and effectiveness of ConNets. So, a CNN or ConNet is a type of feed-forward artificial neural network. The architecture of a ConNet is designed to take advantage of the 2D structure of an input image. A ConNet is comprised of one or more convolutional layers, often with a pooling step, and then followed by more fully connected layers as in a standard multi-layer neural network. So the ConNet layers, I'll talk about them. The first one is conv layer, which will compute the output of neurons that are connected to local regions in the input, each computing a dot product between their weights and a small region they are connected to in the input volume. Now the ReLU layer will apply an element-wise activation function such as max 0x thresholding at 0. Now this leaves the size of the volume unchanged. Pool layer will perform a downsampling operation along the spatial dimensions width and height. Now, FC layer will compute the class scores resulting in volume of size 1 into 1 into n, where each of the n numbers correspond to a class score, such as maybe in the n category. Now, I'll talk a little bit about CNN architecture. So, all CNN models follow a similar architecture as shown in the figure below. So, it's input, then conv layer, then pool layer, then again conv layer, pool layer, and then FC, and softmax. So there is an input image and then a series of convolution plus pooling operations followed by a number of fully connected layers that are performed. If the multi-class classification is performed, the output is softmax. So our CNN compresses a fully connected network in the following ways. It reduces the number of connections, shared weight on the edges, and max pooling further reduces the complexity. I'll also talk about the dense neural network and convolution neural network here. So left, you see a regular 3-layer neural network, and the right, it is a ConNet arranges its neurons in 3 dimensions. So it is based on the width, height, and depth. Now, motivation behind ConNets is that if you consider an image size of 200 into 200 into 3, so a single fully connected neuron in a first hidden layer of a regular neural network would have 200 into 200 into 3. That means 120,000 weights. Now, due to the presence of several such neurons, this fully connectivity is a wastage, and the number of parameters would quickly lead to overfitting. So in a ConNet, the neurons in a layer will only be connected to a small region of the layer before it, instead of all the neurons in a fully connected manner. So the final output layer would have dimensions 1 into 1 into n, because by the end of ConNet architecture, we'll reduce the full image into a single size vector of class scores. Now the applications of CNN, a few of them are listed here, like object detection, semantic segmentation, and image captioning. CNN is now a go-to model for every image-related problem. In terms of accuracy, they blow the competition out of water. It is also successfully applied to recommender systems, natural language processing, and more. The main advantage of CNN compared to its predecessors is that it automatically detects important features without any human supervision. So for example, given many pictures of cats and dogs, It learns distinctive features of each class by itself. Now, CNN is also computationally efficient. It uses special convolution and pooling operations and performs parameter sharing. This enables the CNN models to run on any device, making them universally attractive. Now, the next part of the presentation will be presented by my other teammate. Thank you.
Convolution networks have been applied with great success to the detection, segmentation, and recognition of objects and regions in images. These are all tasks in which labeled data was relatively abundant, such as traffic sign recognition, segmentation of biological images, particularly for connections and detection of faces, text, and pedestrians, and human bodies in natural images. A major recent practical success of Corners is face recognition. Importantly, images can be labeled at the pixel level, which will have applications in technology, including autonomous mobile robots and self-driving cars. Most of the companies are using such corners-based methods in their upcoming vision systems, of course. Other applications gaining importance involve natural language understanding and speech recognition. Microsoft, IBM, Yahoo, Twitter, and as well as quickly growing number of startups to initiate research and development projects and to deploy Covenant-based image understanding products and services. Covenants are easily amenable to effective hardware implementation in chips of while field programmable gate arrays. Several companies such as Mobile, Intel, Qualcomm, and Samsung are developing Covenant chips to enable real-time vision applications in smartphones, cameras, robots, and self-driving cars. Image recognition is one of the assessments in which deep neural networks succeed. Neural networks are registered frameworks intended to recognize designs. Their architecture is roused by human brain's architecture. They comprise of three kinds of layers: input, stowaway layers, and result. These modules are generally utilized for picture characterizations. The object detector consequently learns image features required for detection tasks. Deep neural networks are key in assisting computers with having the resources and space they need to address complex queries and tackle bigger issues. Typical neural networks may just have a couple of hidden layers. Deep neural networks might have many secret layers to assist with tackling an issue and make a distributed representation and language processing. Deep learning theory demonstrates that deep nets outperform traditional learning algorithms that don't use distributed representation in two separate ways. A multi-layered neural network's hidden layers trained to represent the inputs in a way that makes it simple to anticipate in the desired outputs. The network layers word vectors with numerous active components, each of understood as a distinct word characteristics. The debate between the paradigms for cognition inspired by neural networks and logic centers for the problem of representation. Visualizing the lean word vectors. Example of the word representation learned for language modeling is shown on the figure that which is non-linear projected to 2D for display using the T-SON algorithm. A 2D representation of words learned by the English to French encoder decoder recurrence neural networks is shown on the right figure. It is clear that a small number of semantically related terms would necessitate very large training campus since anagrams regard each word as an independent unit. They are unable to realize two word sequence that share semantic relationships.
Recurrent neural networks are a type of neural networks where the results of previous step are fed into the next step computations. RNN uses memory which retains all the information of the previous calculations. What makes RNN different from the traditional neural networks is, in traditional neural networks, we have input and output, and both these input and output are independent of one another. Sometimes there is a need to store the previous step history, which would be required for the next step calculations. In such time, RNN comes into the picture. RNN has a hidden layer, uh, which will be used to resolve this problem. Hidden layer plays a significant role in storing the information of previous sequence. It performs calculations using the weight and bias. this slide, you will be seeing the RNN architecture. The first diagram shows us the simple RNN block diagram. Here we have an input layer called X, and we have an hidden layer called W, and there is an activation function we'll be using for it, and the output is represented as Y. If we unfold the hidden layer, we'll be having multiple hidden layers in it. The first it is showing as YT-1 is the first hidden layer output, YT is the second hidden layer output, and YT+1 is the third hidden layer output. We'll be having activation function for every hidden layer, and and the weights are same for every hidden layer here. RNN converts all the independent activations into dependent activations by providing same weights and batches to all the layers. This will reduce the complexity of increasing parameters and also memorizing each previous outputs by giving each output as input to the next hidden layer. The below function th is used for calculating the current state function. Here tanh is the activation function which is used for eliminating all the negative values of the output. If you look at the formula function there, the WH is called as the hidden layer weights, and HT-1 is the previous layer output. And if we see the WXH there, it is weight of the input layer, and XT is the input. And here YT is the output function, where WHY is the weight for the output function, and HT is the hidden layer output. So the product of the weight of WHY and HT gives us the output. Coming to type of RNNs, there are 4 types of RNN, that is one-to-one RNN, one-to-many RNN, many-to-one RNN, and many-to-many RNN. In one-to-one RNN, this is generally used for machine learning problems which are single input layer and one output layer. Coming to one-to-many RNN, this is generally used for the types layer which has only one input and many outputs. Example of this is image captioning, which has only single file as input but has multiple things to be determined. Coming to many-to-one RNN, this has multiple inputs and only one output layer. Simple example of this is sentimental analysis, because we will be providing multiple inputs here, but the only thing we will be receiving as output is either it is positive or negative. And coming to many RNN, this is generally used for forecasting things. We have multiple outputs and multiple inputs here. This is also called a sequence to sequence RNN. This is used for forecasting purposes like stock forecasting, weather forecasting, price forecasting, etc. Coming to the applications and advantages of RNN. RNN is used in many applications nowadays. The main application of RNN is natural language processing. This is used in emails to predict what is the next sentence that the user is going to write, or giving suggestions to the user in Word, etc. We also use RNN in scam detection. Example of that is we get scam emails and all those things. By clicking the report scam, we don't get the similar type of emails next time. And also we use this in scam detection of credit cards and all those things. Also we use this RNN in forecasting applications such as weather forecasting, stock forecasting, price forecasting, etc. We also use this in speech and voice recognitions. Coming to the advantages of RNNs are used with CNN in extending the powerful pixel neighborhood. Also, we can simulate a set of records in such a way that it is possible to assume each pattern that comes next using the previous patterns.
Yeah, the future of deep learning. Deep learning has attracted a lot of attention in recent years, both in academic and business circles. AI adoption keeps adding value in organization, while deep learning use in business is still at an early stage. But the innovations brought to the table by this AI approach are promising. A real big question is left though: is deep learning is further of future of machine learning? Well, we don't put it that way, as these technologies are not equal, each with its own benefits and shortcoming. Here we like to point out that distinct features of deep learning that add to its popularity. The applications of deep learning. automatic feature extractions and transfer learning. When coming to automatic feature extraction, unlike traditional machine learning, deep learning eliminates the need of manual feature extraction. Neural networks are capable of drawing features out of raw data automatically without human innovation. This is something known as feature learning. Multiple processing layers of neural nets produce different representations of data, increasing the feature complexity with every new layer. Transfer layer learning, another cool thing about deep learning is that you don't necessarily have to train neural network from scratch. Instead, you can option for the technique called transfer learning. In layman's terms, it's when you pick a neural network that has already been trained on one task and reuse it on a new but related program. Major progress in artificial intelligence will come about through systems that combine representational learning with complex reasoning. Although deep learning and simple learning have been used for speech and handwriting recognition for a long time, new paradigms are needed to replace rule-based manipulations of symbolic expressions by operations on large vector. Finally, we expect systems that use RNNs to understand sentence or whole documents will come much better when they learn strategies for selective attending to one part at a time.
The paper that we chose was based from a paper called Deep Learning. This was written by Yan LeCun, Joshua Bengio, and Jeffrey Hinton.